My name is Adam Crank. I'm a math and physics major at the University of Alabama in Huntsville. And my project is upstream wave activity observed at an interplanetary quasi-perpendicular shock. And I was working under my mentor, Dr. Zhao. So interplanetary shocks form when bursts of energetic particles are launched from the sun, like a coronal mass ejection, for example. And they travel at speeds faster than the ambient solar wind. Generally, the shock itself is the boundary between the supersonic cluster of particles upstream of the boundary and the subsonic solar wind downstream. This boundary represents the region where the medium slows down to subsonic speeds, but information transfer between the upstream and downstream medium, which is collisionless in the case of a typical solar wind plasma, will be locally supersonic. So the purpose of the project throughout the 10-week summer interval was to be able to categorize different shocks based on their individual properties, with a focus on a shock event observed between April 19th and April 20th, 2020 by the Wind and Solar Orbiter spacecraft. To begin, we had to calculate several parameters that are used to describe a shock of this nature, with an emphasis on data using data collected by wind, which is pictured here. To parse the spacecraft's data, I chose to use the R programming language. Although R is not computationally powerful, it contains substantial built-in functionality for statistical analysis, making it relatively easy to handle the large data sets collected by these spacecraft. So the first two parameters that would give us insight to the behavior of the shock are the shock normal and shock obliquity. The shock normal is a normal unit vector that gives the direction that the shock is moving in, while the shock obliquity is the angle between the shock normal vector and the upstream mean magnetic field vector. This angle is what determines whether a shock is parallel or quasi-parallel, meaning that the obliquity angle is between 0 and 45 degrees, or a perpendicular or quasi-perpendicular shock, meaning that the angle is between 45 and 90 degrees. There are several methods to determine the shock normal, with the magnetic coplanarity method being among the most prominent. So the magnetic coplanarity method makes several assumptions. First, it assumes that the upstream and downstream magnetic fields are in the same plane as the shock normal, or more simply, that they are coplanar. This is known as the Coplanarity theorem. A second assumption is that the magnetic field, both upstream and down, is stationary, meaning that the direction and magnitude of the field are constant. In this equation, B sub D here represents the average downstream magnetic field strength, B sub U represents the average upstream magnetic field strength, and delta B is the difference between the two. The accuracy of this method is contingent on several factors, namely the instrumentation on board the observing spacecraft and the shock obliquity theta B sub n. In particular, this method fails in cases where the shock is perfectly parallel or perpendicular, i.e. The obliquity equals 0 degrees or 90 degrees. A variation of the magnetic coplanarity method, called the mixed coplanarity method, is used in this report based on wind spacecraft measurement. Here, delta V represents the difference between up and downstream flow speed averages. Another implicit assumption made by the coplanarity theorem is that the velocity vectors are also coplanar with the magnetic field and shock normal, meaning that the flow speed can be used in calculating the shock normal direction. Additionally, the mixed coplanarity method is accurate for obliquities near 0 and 90 degrees. One other method for determining the shock normal is called the minimum variance analysis, or MVA method. Like the coplanarity methods, MVA operates on the assumption that the magnetic field is stationary. This implies that a unit vector in a direction in which magnetic variances are as close to 0 as possible will represent the shock normal. Thus, this method involves minimizing these variances in order to determine the normal shock. The minimum variance or minimum magnetic variance equation is given here, alternatively in matrix form right here. In this equation, M is the magnetic variance matrix, and lambda represents the eigenvalues of M. The eigenvector corresponding to the smallest eigenvalue represents the shock normal. So both the mixed coplanarity method and minimum variance analysis methods return very similar values for the shock normal, which appears to point radially outwards from the sun, implying that this result is relatively accurate. The calculation of the mean upstream magnetic field vector is fairly arbitrary in the R programming language, as is the method of determining the angle between two vectors. Thus, I've calculated a shock obliquity of about 72.5 degrees by both methods. Once again, the results here imply accuracy since they are both very close to each other. And because the shock obliquity is greater than 45 degrees but less than 90 degrees, we can classify this as a quasi-perpendicular shock. A second set of shock parameters can be used to determine whether a shock is a fast or slow or forward or reverse shock. These are primarily the magnetic field, velocity, temperature, and particle number density jump parameters, i.e. the ratios of downstream averages to upstream averages from the spacecraft's reference frame. Of particular note, all of these ratios are greater than 1, meaning that the average values for all 4 of these variables increase across the shock. This is only the case for a fast-forward shock, shown here in the top right, or top left, sorry. By plotting these variables over time, we can reproduce a case-specific chart that appears similar to this diagram. In this chart, with magnetic field strength at the top, flow speed in the middle, and number density on the bottom, we have these gray regions here. This gray region on the left represents the interval we use to calculate the upstream averages of all these variables. And the one on the right is the interval used to calculate the downstream averages. In the center here, we see this clear discontinuity in the data, which occurs at approximately 1:35 on April 20th, 2020. This indicates the shock structure. And the trend in this data lines up with what we expect in a fast-forward shock. Therefore, the shock event observed between April 19th and April 20th, 2020 is a fast-forward quasi-perpendicular shock. Moving on to investigate potential wave activity around the shock structure, we take a look at the power spectral density upstream of the shock. To calculate the power spectral density, we create a vector consisting of the difference between the measured magnetic field data, taken with a 92 millisecond resolution, and magnetic field averages. This new vector consists of magnetic field fluctuations across the upstream interval in the x, y, and z directions. Then we take the Fourier transform of the magnetic fluctuation vectors, summing the squares of the transforms to get the total trace power spectrum in our given interval. By plotting the power spectrum against frequently, shown here, in 30-minute intervals, from midnight to 12:30 in red, from 12:30 to 1 in blue, and from 1 to 1:30 in green, we see that there's a noticeable trend of rising power fluctuations as our interval approaches the shock structure that, as a reminder, occurs at about 1:35. This trend shows evidence of wave activity in the medium just upstream of the shock. So in conclusion, we have classified the shock that occurred on April 20th, 2020 as a fast-forward quasi-perpendicular shock. Additionally, there is clear evidence of wave-like behavior in the medium just upstream of the shock. Unfortunately, the summer term has come to an end before this topic could be explored in further depth. Future work would include analyzing upstream wave activity more qualitatively, as well as examining the downstream medium for wave-like behavior. Additionally, we can apply these classification methods that we use to classify this shock to other cases of shock events that have been observed by similar spacecraft. Thank you for your time.
Hi, my name is Quasi, and thank you for watching this video. Make sure to follow us on our social media at CPH2AL on Facebook, LinkedIn, and Instagram. Bye!